Capacitive reactance is the term given to the way that capacitors will restrict current based on their properties of holding charge and resisting more charge from flowing onto the plates. Now, whereas resistance was a property of a resistor and it just had one number, capacitive reactance depends on the frequency of the oscillating voltage source. Let's say that a 60 Hertz source has an RMS voltage of 120 volts, and it's connected to a 4 farad capacitor. We'd like to find the capacitive reactance in this circuit. So the reactance has the letter X, and we'll put a subscript C to make it clear that it's a capacitive reactance. We'll see later that there's another type of reactance, inductive reactance, which is caused by components called inductors. But for now, we don't have to worry about that. For now, we'll just focus on capacitive reactance, which has the formula 1 over omega times C. C, of course, is the capacitance of the capacitor, and omega is going to be a property of the circuit itself, the angular frequency with which it is oscillating. We can see here that the larger the angular frequency, the smaller the capacitive reactance. In other words, the slower that the circuit is oscillating, the more resistance there will be to current flow by this capacitor. But the faster the oscillation of the current, the smaller the reactance will be. This is a source that's oscillating fairly quickly. It's 60 Hertz, so 60 times per second. Since we have the frequency, we'd like to use the other formula for reactance, which is 2 pi f times C. All right, so let's plug in 60 Hertz. And it's a 4 farad capacitor. Okay, so I'm getting a reactance of 0.00066. And the units of reactance will actually be ohms, because it is going to be something which impedes current. And now we'll use Ohm's law, but it's applied to the way that a capacitor will resist current. So the formula for Ohm's law in this case will be VRMS equals IRMS times XC. When we had a resistor in series with an AC source, we would have used V equals IR. But since we have a capacitor, we'll use V equals IX. All right, so that means that our current is going to be found by dividing the RMS voltage by the capacitive reactance and I'm getting 181,000 amps. It's hard to believe, but the AC current in this setup would be enormous, even though there's this gap in the circuit. The reason why it would be enormous is because any given electron is fairly free to vibrate back and forth, and not enough charge builds up on these plates in order to stop the electrons from vibrating on the plates and off the plates. So the current still remains very large in this situation. If we want to change the amount of AC current that's being developed, we can change the capacitive reactance. And one way to do that is to introduce a different capacitance. The old capacitor was 4 farads. Now we'll have a new capacitor of 8 farads, and let's see how the current changes. We'll calculate the new capacitive reactance. We have the same frequency of oscillation for our source. But as we can see, increasing the capacitance is going to decrease the overall reactance. All right, now our reactance is 0.000331 ohms, so it cut the reactance in half. And how will the current respond? Now we have a capacitor in the circuit which is even more capable of holding charge on it. So that will provide even less obstruction to current flow. And those electrons will be even more able to just vibrate back and forth onto the plates and off of the plates. Let's see what current we get this time. Now I get 362,000 amps. We should also think about the limit of what happens when the capacitance goes toward infinity. Well, if capacitance goes toward infinity, then according to the formula here, we would have 1 divided by infinity, and our capacitive reactance will actually go towards 0. When that happens, the current will go toward infinity. So we would have a short circuit in that case. It would mean there would be no opposition to alternating current flow. It would mean there'd be no opposition to AC current flow. What about, on the other hand, if the capacitance goes towards 0? Well, this would be a capacitor that can't hold any charge whatsoever. The capacitive reactance then would go toward infinity, and the RMS current therefore would go toward 0. It would be like having a break in the circuit, and it wasn't really a complete circuit at all. So we would have no current in that case. In order to draw these cases, what we're talking about is having an enormous capacitor with a very small distance between the plates. If the capacitance goes toward infinity, then there's supposedly unlimited potential for these plates to hold electrons. So the electrons would easily shake back and forth in the circuit, thus creating a large alternating current. On the other hand, though, if we have an alternating source attached to plates which are minuscule and the gap between them is huge, if the capacitance goes towards 0, then there won't be any ability for current to flow in this circuit. And so here, the I goes towards 0. Here, the I goes toward infinity.